And we are learning classwork 3.6. We are now solving log equations. Yay! So there are two situations you're going to run into when you solve log equations. One of them is you have the same based logarithm. You're not going to get different based logarithms, by the way, not in this class. And they are basically just equal to each other. Essentially, what you can do is you can b to the power both sides, and that will undo the log base b's, and you get x equals y. So case one is if you are having that form, log bx equals log by, you can go straight to x equals y. You don't have to show me how you are getting there. You just need to get there. So some examples. Oh, also extraneous solutions can come about with logarithms because of the domain. Logarithms can only have positive numbers go in them, and that's actually the only thing you need to check to determine extraneous solutions, is to make sure that you're only getting positive numbers going into the logarithm. So here we go. We have log base 2 of something equals log base 2 of something else. You can go straight to their insides must be equal. X plus 3 is equal to 5 times x. And if you want to see it, I'm basically 2 to the power in both sides, which cancels the operation of log base 2ing stuff. And then to finish solving, I'm going to subtract x, and I get 3/4 is what x is equal to. To check for extraneous solutions, all I have to do is go back to the insides of my original logarithms and make sure that if x is 3/4, all logarithms are getting positive numbers put in. So you don't have to actually calculate. You just need to ask yourself, if x is 3/4, is 3/4 plus 3 positive? And yes, it is. Is 5 times 3/4 positive? Yes, it is. That's all you need. They're both greater than 0. It is a solution. It is not an extraneous solution. Done deal. Number two. Number two is not in the form of log equals log, but you can get into that form pretty quickly if you realize you can multiply the denominator over to the right, and then you have log of 2x equaling log of 3x plus 2. Hopefully you remember, if the base is not written, it's understood to be base 10. And you can go straight to the insides have to be equal. Technically, I am 10 to the power in both sides, undoing the operation of logging. And I get 2x equals 3x plus 2. Yes.
How did you get from log 2x divided by log blah, 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 and then how did you turn that?
I multiplied by the denominator. So I multiplied both. I just multiplied that over.
Oh, yeah. Since it's 1.
Yeah. And now I need to isolate my x. So if I subtract 2x to both sides, I will get x on the right, subtract the 2 over, and I have a possible solution, but I have to check for the extraneous. Again, see what's inside the original logarithms. The x that you get as an answer has to make both of the insides be a positive number. And you can see pretty quickly that 2 times negative 2 is not positive. That means that this is an extraneous solution. And that means our final answer is that there is no solution to that equation. But again, the only thing you have to check is that the number you get when you solve, that it makes positive numbers inside of all the original logarithms. And now we are ready to prep for case 2. And everything I'm doing with this prep, we have looked at already. I just want to reiterate it and make sure that this is clear. So if you have a pair of inverse functions and you put one of them inside the other, that is how you undo every operation in a function. And whatever goes in originally is what you end up with, no matter which direction it goes. Now, what is the inverse function of b to the power of x, where b is a number? And then you guys say that's I guess you're not in the mood to type it. Log base b of x. If I use the principles that we have right here in these two equations, that gives me the other two important properties of logs. You get a total of 5 important logarithm rules that you need to know. You really don't need to know any other property that you run into. So I am going to put these down. If I look at it this way, then it is the function b to the power of x, but instead of having an x, I'm putting in the inverse function, which is log base b of x. I don't need the parentheses, but I put it there to emphasize that it was replacing the x variable. So again, if you see b to the log base b of x, you get x. And we've already played with that a bit, but this is so important, it's good to emphasize it some more. Oops. I touch my screen and it just decides, oh, you want me to do this. Okay. Then the other way around, if I start with the inverse, then that's log base b of, but instead of putting x, I substitute in b to the x power. I am supposed to get out x. And it doesn't have to have the parentheses. Again, that was for emphasis. And the more you understand these properties of inverse functions, the less you have to memorize these rules. When I combine those two with those other 3 properties, again, that is everything that matters. So I am going to show you. These are the only log rules you need to know. We have the 2 inverse rules we just discussed. And additional formulas, basically, it kind of comes out naturally, but be aware that log base b of b, the exponent is an understood 1. So that's why we're getting 1. And if I have log base b of 1 itself, what exponent causes b to the x to equal 1? And that would be exponent 0. So these are additional formulas to make sure you're aware of, but again, they do come out of these inverse formulas. And then we have these 3 log rules that help us to either expand or condense logarithms. And there are times where we want to expand and there are times where we want to condense. In this class, you're just learning how to do it. So let's get back to the notes. And I want to, the reason I brought this out, the inverse properties, was because you can use that to solve your equations. You don't need to memorize any extra additional formulas at all. So here we go. If you have log base b of x equals a, if that is the situation you are in with solving an equation, I look at it as I am going to b to the power both sides of the equation. The left side of the equation is log base b of x. The right side is a. So I wind up getting ln x, because of the inverse properties, is equal to b to the a power. Now, if you're ever taking a standardized test and it asks you to write a logarithm in exponential form, this is what it's wanting you to do. All right, now let's solve some equations. Woo! For the first problem here, number 3, I want you to see that I have everything inside of that logarithm on the left side. Compared to 5 and 6, I have a subtraction of 2 logarithms on 5. On number 6, I have a multiplication outside the logarithm. 3 and 4, I don't have either of those situations. That means I'm ready to undo the logarithm. If it's a base 2 logarithm, then I am going to 2 to the power both sides. The inverse operations cancel, leaving me with what was inside that logarithm, 5x minus 1. On the other side of the equation, I have 2 to the power of 3, and 2 to the power of 3 is 8. And now it's time to do a little bit of add subtract. So add, I get 9, and divide by 5. I have a contender for solutions, but I need to make sure it's in the domain of the logarithm. So I look at the 5x minus 1, and I don't need to calculate. I just need to think about whether x being 9/5 makes a positive number or not. So do you think 5 times 9/5 minus 1 is a positive number? It is. Wait, 4/5. Do you mean 4/5? When I added 1, I got 9, so it should be 9/5. And then I'm going to move on to number 4. Here we go. This one is a log base 3, and it's a condensed logarithm already. So I 3 to the power both sides. That means these two operations cancel, and the inside of x squared plus 1 is left over. And then on the other side, I have 3 to the power of 2, so 3 squared is 9. Then subtract 1. And if I have x squared equals a number, I've got to remember to do plus or minus. And you guys know how to simplify that. This becomes plus or minus 2 root 2. But I've got to check and make sure that they make positive numbers in the logarithm. So I go back to the beginning, I look at x squared plus 1 and go, hey, you know what? If you square a number and then you add 1, you are definitely positive. I don't even have to try. I don't have to look at these numbers. Every x that I could possibly put in will make a positive number with x squared plus 1. So I have 2 solutions, and there they are. Yay! Woo! We're logging along. Okay. Now these problems, you have to make sure you have a condensed logarithm before you undo the logarithm. There is a reason why this is set up as two cases. And I want to go back and repeat myself on this. The first case, you have logarithms of the same base on each side of the equation. They are completely condensed logarithms and they are equal. In that case, their insides are equal. That's case one. The other case you can run into is a condensed logarithm equaling a number. And in that case, you undo the logarithm by b to the powering both sides, and then you're on your way. But the logarithms have to be condensed to do that. That is going to be your goal, is to have a condensed logarithm and then do one of those two cases. So, number 5. If I am subtracting two logarithms, how does that condense? And I'm hoping you are thinking or saying division. Good. Now I want to step back and look. Is this a condensed logarithm equal to a number? It is. So I'm ready to undo the logarithm. I can undo log base 5 by 5 to the powering both sides. Inverse operations cancel. And I'm left with 9x plus 14 over x minus 1 equals 5 squared, which is 25. I've still got a little bit more work to do. So I need to multiply both sides by the denominator. And now I have 9x plus 14. And I'm going to distribute the multiplication over the subtraction, 25x minus 25. And now we're really on our way. So I'm going to subtract 9x to both sides, giving me 16x on the right. I'm adding 25 to give me 39 on the left. And 39 over 16 is my lovely value of x. Now I've got to check. Does it make original insides of logarithms positive? So 39 over 16. You should see that this one definitely we're in the clear. If x is a positive number and I multiply it by 9 and then add something to it, it's positive. With minus 1, with x minus 1, I just want to look at this number and go, hey, it's bigger than 1, so that means positive. It has been checked. And that means this solution works. One more to go, and I believe that's the end of the classwork. Woohoo! I have to, is this a condensed logarithm, number 6? When we just sit down and look at it, is it condensed, ready to be undone? Correct. It is not condensed. So my first thing is to turn the multiplication into an exponent, the rule that we learned yesterday. So that means I have log of x plus 6 to the 1/2 power. Now, do you recognize what is 1/2 power? You're more familiar with it as, I couldn't hear you. Okay, yeah, square root. And I think I heard something about radical. Yeah. So I'm just going to go ahead and rewrite it that way. I don't have to. And now I'm in the situation of a log is equal to a log. So this is actually not the case 2. This is going back to case 1. And what is the understood base of that logarithm? Good, 10. Technically, while you don't have to say this, I'm 10 to the powering both sides, which kills both logarithms. And I have the square root of x plus 6 is equal to just plain old 7. And then how do I undo the square root? Yep, I square both sides. And that gives me x plus 6 equaling 49. Subtract 6 to get 43, and I have to check. Go back to the original logarithm. I've got an x plus 6 inside one logarithm. That 7 is positive, no x's, so it's good to go. If I plug 43 into this x, I'm going to get positive going into the logarithm. So we've got an answer. And that's how you solve log equations. We're almost done learning what we need to learn with this unit. Tomorrow, I'm just going to talk to you a little bit about using calculators and doing a little bit more with equation solving. The hardest part, though, I think is what you experienced yesterday. And I want to go back and make sure to talk you through some of that. So going back over to 3.5 and looking at the homework from that. I'm guessing that there were a lot of struggles that you guys were having in getting through the homework. And right now I'm showing 6 problems. Of those 6 problems, would you like me to talk you through any of them in particular? Is there anyone in particular that you want me to talk you through? Shall we go through number 6? Okay. Well, corrections are due tonight, so this will be useful. And if you don't see the answers, I can show you real quick the answers. And I'm basically going to take you through what's here. But I'm going to go back to homework and just talk through that one. That one is the hardest one. And the directions are to expand. I've got to remember that this is a base 10 logarithm. For starters, when you have this big division sign, that turns into a subtraction of 2 logarithms. So I have log of the numerator minus log of the denominator. Then I need to look at each of those 2 logarithms and figure out if I can expand them. You can expand a logarithm if you see inside the logarithm multiplication as well as exponents or division. So I see multiplication in this first logarithm. And that means I can split this up into 2 logarithms that I'm adding. So log of x plus log of y. I want to be very careful about this minus sign, so I'm going to put minus in a parentheses. And the next thing that you want to see is that you have 100 multiplying by z to the 3rd power. That means that you can split the addition and have 2 logs that are adding. Log of 100 plus log of z cubed. And while I'm at it, I am going to distribute my subtraction. So I'm going to add the opposites. Now I want to look at each of these 4 logarithms and see if there is more I can do to take from inside the logarithm to outside of it. For this first one, I only have x in there. It's done. Second one, I only have a y in there. It's done. For this next one, I have a 100, and this is a log base 10. What is the log of 100 if it's a base 10 logarithm? Good. So as I write the final answer, I've got my log x plus my log y. This becomes minus 2, and then minus. And for this last logarithm, you want to see that you have an exponent. That exponent turns into multiplication outside the logarithm. And then I no longer have that exponent inside. This is as expanded as you can get. And there it is. Now, yesterday you guys were getting a little bit, you're having a little bit of a hard time when I was going through all 3 rules at once. Are you feeling more comfortable today? More comfortable? Are you feeling totally comfortable? Mixed there. Okay. And that's good. And that's why I don't want to be giving you a test this week. You need to play with these for a little bit to get to know them and really understand them, instead of this just being a lost lesson that flies into madness and you go, I don't ever want to see that again. You might say that anyway, but hey, no, logs are your friend. They're friendly. Okay. Do you want to see any of these problems done from the homework? Should I do number 10? Talk you through number 10? Excellent. Okay. Keep your friends close and your logarithms closer. When I am condensing a logarithm, I find that to be easier to know when you're done, but it also creates this problem. I have base 2 logarithms. I need to change the 4 into a base 2 logarithm. But remembering those inverse properties, if I have log base 2 of 2 to the power of 4, that is the same thing as just plain 4. And now I'm going to start combining these together. Let me erase some of this excess. I'm going to first bring these 2 together. You have 2 logarithms adding, so they condense into a single logarithm if you multiply their insides. And then I'm going to write out that I have minus, and I have 2 minuses. So what is a good idea is to go minus parentheses and then have this be addition. That means I have log base 2 of, and what is 2 to the 4th power? Mm-hmm, 16. So I'm going to start writing that as log base 2 of 16. And again, I am pulling this subtraction out so that I have addition with 5 times log base 2 of z. Make sure that you notice that you have a number multiplying to this last logarithm. And it's very important that you're aware that you cannot combine them with the addition until they have no number multiplied in front of them, except for 1. So I use the rule that a constant multiple turns into an exponent inside the logarithm. So I have log base 2 of 16 plus, and then this is going to be log base 2 of z to the power of 5. Now I'm ready to bring together these two logarithms with addition. And that becomes multiplication inside one logarithm. Now I don't have to have this parentheses here around the xy, but I'm really close to done. At this point, I have two logarithms that are subtracting. They condense into one logarithm with division. And I know I'm condensed because there is nothing outside the logarithm. Everything is inside that logarithm. Yay! Today you are quizzing on section 3.4. And with section 3.4, that was when we had the rules for both the sum and the difference of logarithms. But we didn't yet have the issue with the exponents turning into multiplication. And let me point out the homework answers. There we go. So in today's quiz, you need to expand expressions. I am not going to ask you to go as far as this. Other than that, I expect you to expand your logarithms and also condense logarithms until everything is inside of one logarithm. Also, I've got a multiple choice problem for graphing logarithms with a base between 0 and 1. So make sure you familiarize yourself with what that logarithm graph looks like if you have a base between 0 and 1. We've got our parent graph. And then we see that parent function multiplied by 3. And then taking that 3 times log base 1/4 and translating it left 3 up 2. I'm going to ask you, or you need to be able to find 2 accurate points when the test comes around. The parent graph, make sure you understand it always has the x-intercept 1, no matter what base you're working with. If you have a base that is a fraction, and I'm only going to give you fractional bases with 1 divided by a specific number. So 1/4, 1/3, 1/2, 1/5, anything like that. And it's difficult to plot the point that I usually say to plot with the bases that are greater than 1. Because with the bases greater than 1, what I told you to plot was the actual base number as an x-coordinate will have a 1 come out as its y-coordinate. If your base is 1 divided by a number, okay, if my base is 1 divided by a number, I can more easily plot the point of the reciprocal of that base. So the reciprocal of 1/4 would be 4. If I plug 4 into that x, what is the answer to that logarithm? So what exponent does 1/4 need to have in order to get out an answer of 4? Yep, -1. So if x equals 4 on this parent graph, y is equal to -1, that's an easier point to plot than trying to plot the fractional 1/4, 1. And that makes it easier to stretch the graph with multiplication. And I want to make sure I'm going to erase these so that I can color code. When I multiply outside the function by 3, I multiply the y value by 3. This y value is 0, so it's not going anywhere. For this point, the y value is -1. -1 multiplied by this 3 will be -3, but I keep that x equals 4. And then if you want to deal with the fractional one, that y value is 1, and if I multiply it by 3, I will get 3. It will keep the x coordinate of 1/4, and so stretching it. And then after you do that stretching, take a minimum of 2 points and shift them, and you're good to go. All right. Do you have any questions, things you still need some help on? Trying to think. This class is over in 20 minutes.
I have a question.
Uh-huh. Absolutely, I can do that. Let's take a look.
Can you go over number 4?
Mm-hmm. Yep. Yes, I can help you out. I can do 3 also. When you're solving your log equations, make sure they are condensed. That is your first priority. You want to see the subtraction, and remember that you can condense subtraction between 2 logarithms to being 1 logarithm with division. And remember that you cannot get rid of your logarithms until you have condensed logarithms. Do you see that we have a log on both sides and they are both condensed? So now I can, the understood base is 10. I can 10 to the power both sides, which really just gets rid of both logarithms. You don't have to show that work. And we get x minus 3 and this fraction.
On my work, would I have to write like log 10 and I just like put my first like x minus 3 equals 7 over.
Yes. Yes, you can go straight to that. Now, I've found over time that a lot of people get stuck here, but as soon as they see it, they don't know why they were stuck. But just remember, if you see a denominator, what can you do? You can multiply both sides by that denominator. And then these will cancel, but I've got to make sure to multiply this binomial correctly. So I want you guys to tell me, what do I get when I multiply those two together? The x plus 1 and the x minus 3. And that's part of it. If you don't see the whole thing, do the box multiplication. X plus 1 times x minus 3, because you have to use a double distributive property. And if you go through that, you will see, yeah, you got it. It's x squared minus 2x minus 3. This is one of the most common algebra mistakes that people make, is not fully distributing. Then 7x minus 23 is what it's equal to, and we're getting there. If you have a quadratic equation and you need to solve that quadratic equation, there's a key step right now that you need to do. Before you go into factoring, what do you have to first make happen? I need my quadratic, there you go. I need my quadratic to be set equal to 0 before I factor. 0 is the only number that if you're multiplying two numbers and the answer is 0, then if either one of those two items multiplying are equal to 0, it's correct. 0 is very, very special that way. I've got x squared. I need to subtract 7x over to the left side. And I need to add 23 over to the left side. And then it's time to factor. I'm looking for two numbers that multiply to make positive 20. And when I add them, I get negative 9. And I think I saw some people with that. And now that I have the two factors equaling 0, this will be true if x minus 5 is 0. And it will be true if x minus 4 is 0. But do you remember what you still have to do? What do you still need to do? See if it works. And what is it that is all you need to look at? You don't need to go through and solve the whole thing. You just need to look at the insides of each logarithm. Any number that is a solution has to make positive numbers go in the logarithm. When we undo the logarithm, we open up the problem to a larger domain than a logarithm has. That's why we have to check for these extraneous. Now, I don't need to know what x minus 3 is. I just need to know, is it positive for both 5 and 4? X minus 3 is positive for both, right? Check. 7x minus 23. Is that positive for both of these? Seven times 5 is 35. We're good there. What is 7 times 4? What is 7 times 4? 28.
28.
Excellent. Thank you. And that is going to give me a positive number when I subtract 23. So check. That's good. then x plus 1, and hopefully you can see pretty quickly they are both coming up positive. That means both of them are solutions to that equation. Do we have a quiz? Yes, we do have a quiz today. Okay, how about I open up that quiz if you have a doctor appointment in like 5 minutes? And tell you what, I'm going to say real quick for number 3, because it was asked for, make sure you condense over that addition sign. And then you're able to undo the 4 to the log base 4s. And after that, you'll condense with the addition by turning it into multiplication using the log rule. Realize you've got to spend time looking at the log rules and getting familiar with them. Yeah. And then at that point, you'll 4 to the power both sides, and you'll be dealing with a quadratic like you were with 4. Okay, I'm going to stop because we've got 10 minutes